In this section we're going to talk about tools for reasoning about the correctness of programs. Let's look at the program about which we reasoned in the launch. What do we have here? Well, in the yellow boxes we have that we start in a state where 0 is less than or equal to n, and if we then set s equal to 0, we end up in a state where s is equal to 0 and 0 is less than or equal to n. If we look at that in isolation, this is what it looks like. Now notice that it is the assertions together with the actual command that either is correct or not correct. The command by itself is just a command. It's only in the context of what the input is, 0 less than or equal to n, and what you want the output to be, s is equal to 0 and 0 is less than or equal to n, that we can reason about whether this particular segment of the code is correct. Now another way of presenting this is that we have a precondition, 0 is less than or equal to n, a command, s is set to 0, s becomes 0, that's what the colon equal stands for, and then a postcondition, s is equal to 0 and 0 is less than or equal to n. And more abstractly we can write this as the predicate q, the command s, and r, the precondition, the command, and the postcondition. Let's look at another example. If we now want to reason about the correctness of the assignment of 0 to k, we might pull out the assertion that initially s is equal to 0 and 0 is less than or equal to n, the command which sets k equal to 0, and then the postcondition of what we want to hold afterwards, which is that s is equal to 0 and 0 is equal to k is less than or equal to n. Again, we can write this more succinctly as follows, and more abstractly as a precondition q, a command s, and a postcondition r. We see this all over the place. Here we have a precondition that says that at the top of the loop s contains the sum of the first k elements of b, a command that actually consists of two simpler commands, one that sets s equal to s plus the contents of the kth element of b, and then the increment of k to k plus 1. And then the postcondition is that we want to again be in a state where s is equal to the sum of the first k elements of b. Isolated, we look at that like that. And now we notice that the command has become a little bit more complex. It's a composition of the two statements. When we write it more succinctly, we put a semicolon between the statements so that they are more easily identified. But abstractly, we're still looking at a predicate q, a statement s, and a postcondition r. We could look at the entire program. We have a precondition that 0 is less than or equal to n. We have a postcondition that says that we want s to contain the sum of the elements of b. And everything in between is now our command, capital S. So this is known as a Hoare triple, named after Sir Anthony Hoare, who introduced this first. The Hoare triple QSR holds if and only if S, when executed starting in a state that satisfies predicate Q, completes in a finite amount of time in a state that satisfies predicate R. Here's another way of thinking about this. The precondition Q describes the state of the variables before S is executed. In other words, it describes what must hold about the input if S is to be executed. The postcondition R describes the state of the variables after S is executed. In other words, it says something about the output of statement S. And then QSR, the Hoare triple, holds only if execution of S correctly changes the state of the variables as described by Q to a state as described by R in a finite amount of time. What the concept of the Hoare triple gives us is a formal way of asserting the correctness of a program segment that has been annotated with a precondition and a postcondition. Notice that the Hoare triple shows up in the logo for our course, so obviously we believe it to be extremely important.